In this video, we're going to be looking at a certain mathematical structure of vectors and exploring whether that structure forms a vector space or not, according to the definition of a vector space. The structure we're going to look at consists of ordered pairs of real numbers This is how the vectors are going to look like. The A and the B are arbitrary real numbers. So, for example, the vector 1, 1 is there, the vector 1, 0 is there, the vector 0, 0 is there, the vector 0.5 pi is there, and so on. However, we're not going to be using the usual operations for this structure as we do with the usual space that's called R squared, the Cartesian plane. The addition of vectors is still going to be the usual one. So the vector AB plus the vector CD will be defined in the usual way as the vector A plus C B plus D. However, the scalar multiplication is defined in a different way than the usual one, and namely, if we have a scalar k, so if k is a real number, then k times vector AB will be defined not as k times A comma k times B as it usually would be, but rather as k times A comma 0. So basically, when we multiply a vector by k, the first coordinate gets multiplied and the second coordinate becomes 0. What we want to figure out is whether this mathematical structure with the type of objects we identified here, which are pairs of real numbers, together with the law of addition we identified here and the law of scalar multiplication, whether these three ingredients form a vector space or not. They certainly provide the structure we need for it to form a vector space, but a vector space is given not only by a structure, but also by certain properties, certain axioms that should hold. Well, one of them, perhaps the most basic one, is that if we have two vectors, their sum should still be a vector in this set that we've identified. And indeed, in this case, we see that this is so. You see, if we take two ordered pairs, A, B, and C, D, their sum, being defined like the way it is still an ordered pair of real numbers. Surely A plus C is a real number, and B plus D is a real number as well. And also, if we take a vector AB and multiply it by scalar, with the way we define multiplication, still gives a vector in the set, because an ordered pair k times A comma 0 is still an object in the set. There is actually a nice explicit way of writing out this set, the set that we're considering for this example. We will call it V, and using the set theoretic notation, it can be written out as follows. What this notation means is the following. Well, it means what we said it would mean. It means the set of all the ordered pairs A, B, where A and B are real numbers. But I'm just going to indicate to you how you can read this notation. So the curly brackets here, they indicate that we are forming a certain set. Now, this part here shows us the shape of objects that are being included in the set. So at this point, before the vertical bar, we are saying that this set is going to include these kinds of objects, but not necessarily all of them. And which of the objects of this shape are included, that is specified after the vertical bar. And what we have here after the vertical bar is a requirement that both A and B must be real numbers. So for example, an ordered pair consisting of an apple and a bicycle would not be included in the set because neither an apple nor a bicycle is a real number. So although this meets the first requirement of the shape of an ordered pair, it does not meet the second requirement of the property that the ordered pair should have in order for it to be an object in this set. Alright, so we have this set of such ordered pairs, the ones where A and B are real numbers, and we've defined a way of adding them, and also we've defined a way of multiplying them by scalars. And what we want to do, as we originally set out to do, is to check whether this structure forms a vector space. So what we have at the moment is basically three things, right? We've got a set V, we've got addition defined on this set, and we've got scalar multiplication defined on it as well. Alright, maybe a remark is in place here. Notice that the addition symbol and the scalar multiplication symbol looks exactly like the ones we're used to, although we are giving them a different meaning in this example. For example, specifically for multiplication, we're not giving it the usual meaning how we multiply a vector by a scalar, but rather a different one given by this equality. And that's fine as long as we remember that the meaning of this notation is going to stay only within this example, and we're not going to reuse it outside the example. Outside the example, we will be using these symbols for the things that they usually stand for. And even inside the example, depending on what objects we're working with, the symbol obtains corresponding meaning. For example, already in this equality, the left-hand side dot stands for the scalar multiplication we're defining, but the right-hand side dot stands for the multiplication of real numbers. In a similar way, the left-hand side plus stands for the addition we're defining on vectors, but the right-hand side one stands for the addition of real numbers. Now, this is a common abuse of notation in mathematics, to use the same symbol for various different things. And then the task is, of course, to figure out, depending on the context in which the symbol is used, by which meaning the symbol is being used. And the idea is that whenever the same symbol can mean multiple things, it should be quite clear and simple and easy for the reader to figure out what meaning of this symbol we are applying in that context. And if it is not, then the meaning should be clarified. Great, so what we've got now is what is called a mathematical structure, a thing with things in it. So we've got a thing with three things in it, a set V, a rule for adding objects in V, and a rule for multiplying real numbers by those objects. We call these objects vectors, although maybe we shouldn't, because after all, we might establish that this thing, the thing inside the the blue box, is after all not a vector space. And if it is not, then we're not allowed to call its objects vectors. Although the same objects, the ordered pairs, might appear as vectors in a different structure, which turns out to be a space indeed. And indeed they do, right? In the space R squared, where everything is the same except that the scalar multiplication has, instead of the 0 here, k times b. In that case, that thing is a vector space. So then AB, ordered pair, will be a vector in that vector space. But whether it will be a vector or not in here will depend on whether this thing is a vector space or not. And that's what we're going to look at now. We've already remarked that the most basic axiom of a vector space, that it should be closed under the operation of addition and scalar multiplication, is satisfied. And now let's start looking at the other axioms. We're just going to go through them one by one, and in each case trying to check whether the addition and scalar multiplication, the way we define them, whether that makes the corresponding axiom true or not. All right, so the first axiom we're going to look at will be the one that talks about commutativity of addition. Let me write out the axiom before I check whether that axiom holds in the space we're considering now. Well, in the set we're considering now with the operations given, we don't know yet it's a space, right? Until we check those axioms, we can't say that the thing we're working with, this triple v plus dot, we can't say that's a space until all the axioms are verified. According to the axiom of commutativity of addition, what we need to have is that whenever we've got two things in the set, and let me go back to this slide to remind myself what notation I use for representing the things. Okay, it's an ordered pair with the A and B representing its components. So the ordered pair itself will I will then write it in general terms as x or y. So let's say we've got x and y which are in V. This little symbol here, which is an artistic form of Greek letter epsilon, tells me that the x and y are objects in the set V. The usual terminology there is element. So x and y are elements of V. So when x and y are elements of V, we need x plus y to equal to y plus x. And this we need for all the x's and y's in V. Now, in the space we're working with, which is not yet a space, right? In the thing we're working with, the x and the y, they have this form. So x is some ordered pair AB, and y doesn't have to be the same ordered pair. It can be another one, but it could be the same. So let's call it CD, where A, B, C, D are real numbers. And according to how we defined addition in this vector space, x plus y is going to be, so let's actually calculate what it's going to be. It's AB plus CD, and by the way we defined addition, this is going to be A plus C, B plus D. Now y plus x, okay, so what am I doing here? I'm trying to evaluate each side of the equality I'm trying to prove, and then we're going to see if the two sides match. Y plus x is going to be CD plus AB, which is C plus A, D plus B. And what we want now is for these things to be equal, and the question is if they are or not. Well, what are these things? These things are ordered pairs of real numbers. Two ordered pairs are equal when they have the same components. So the equality of these ordered pairs reduces to equality of their components. Is A plus C equal to C plus A when A and C are real numbers, and when by plus we mean the usual addition of real numbers? Well, of course, yes. And the same works for B plus D. It is equal to D plus B. And so then because of the components being equal and the whole ordered pairs are equal, and that makes x plus y equal y plus x, and that makes the axiom true. So this specific axiom for the structure we identified actually works. Addition is commutative. Great. Now we're going to move to the next axiom, and I'm going to skip over that a little bit. The next axiom claims that addition of vectors is associative, and I'm going to now make a statement that by exactly the same methods as we used in the previous case, we can establish that this is indeed so by the fact that addition of real numbers is associative. You see how in the previous case, commutativity of addition of vectors reduced to commutativity of addition of numbers. Why? Because addition of vectors was defined in terms of addition of numbers. We just had to add two ordered pairs, we just had to add the corresponding components. So then that's how the axiom for the vectors reduced to axiom for the numbers. And for the numbers we know addition is commutative, and therefore it is commutative for vectors as well. This exactly the same strategy works to establish associativity of addition of vectors in this structure. Great. The first two axioms hold. Let's look at the third one, which says that in the structure we need to have a certain vector called a zero vector, but it's only called a zero vector after the following property holds. And the property that needs to hold is that if we are given a vector x in V, then x plus 0 needs to be equal to x, and that needs to be equal to 0 plus x. And of course, once we know commutativity is true, 0 plus x and x plus 0 will be equal to the same thing, so we don't necessarily need to write this out separately. That reduces the amount of work we need to do, so we just need to check that x plus 0 is equal to x. But the question is, what is 0? And you see, we cannot choose a 0 specific to x. This has to be some fixed vector in the structure. It has to be the same vector for all the x's. It has to be basically a constant vector. Okay, well, with the way that addition was defined in the previous remarks, how properties of addition of vectors reduce in this example to properties of real numbers, we can maybe perhaps make a guess that the zero vector should be the order pair 0, 0. And then with that zero vector, we will be able to check that x plus 0 is x. Indeed, x plus 0 will be, when x is some vector ab, x plus 0 will be ab plus 0, 0. And by the way we define addition, this will be a plus 0, b plus 0. And of course, for numbers, a plus 0 is a, and b plus 0 is b. So that thing will be ab, which is x. And so we've checked that x plus 0 is x. And so, in this manner, we can continue checking the other axioms, and many of them would hold, but some of them might actually fail. Let me skip over the following one as well, because that one will also quite easily hold. So what we need there is that for each vector x, we need another vector which will be called minus x. And that minus x needs to have the property that x plus minus x is equal to 0. And that also needs to be equal to minus x plus x, but by commutativity we know this will be true anyway. So what we need now is for an order pair AB, we need another order pair that can only depend on this given order pair, called minus that, so that the sum of x and that will be 0. And of course, it's clear that what we need to do here is to take an order pair minus a minus b, and things will work quite well, just as they did in the previous cases. So skipping over that, this is also true in this structure. The next axiom, now we're basically done with the axioms that deal only with addition, and because the addition was defined in the usual way, that's why things work out well. The new thing about this structure is the scalar multiplication. So that's where we expect to have something uncommon going on, and we need to very carefully now check every axiom to make sure that with the new way of defining scalar multiplication, things are still fine. And so let's look at the axiom k times x plus y being equal to k times x plus k times y. Now this should hold for any real number k and for any two vectors x and y. Okay, so once again, let's say x is some vector ab, y is some vector cd. Let's compute what will be each side of the equality we want to establish. So what will be k times x plus y? Well, k stays the same in the first step of calculation, x is AB, so we write AB there. Don't forget that bracket there, because the whole x plus y is inside brackets. And then y is CD, so we keep that there as well. And now, what we're going to do here, in here, we're going to use the definition of addition we have for this structure. So then, this will be k times a plus c, b plus d. At this point, we can remove the brackets here, because it doesn't make sense to keep double brackets when single bracket already shows how the expression is grouped. And so what we've got here is k times that, and before we had k times that. Sometimes we omit the dot symbol, as we do with usual multiplication. So this should have been dot there, and dot here, and dot there, and dot everywhere, right? Okay, so what is k times a plus c, b plus d? Now, remember how we defined multiplication by scalar? K times ab was supposed to be equal to k times a, 0. And this is not only in the case when our numbers are represented by letters a and b. This is a general rule that tells us how to compute any ordered pair multiplied by a scalar. And in this case, the ordered pair we have consists of the first component, not just a, but a plus c, and the second component is b plus d. What the rule tells us is that when we multiply by a scalar, we should take the first component and multiply that by the scalar, and keep the second component to be 0. So that's what we're going to do here. This will then be k times a plus c, and in the second component we must have 0. And that's where we can perhaps stop calculation for the left-hand side. Now, what about the right-hand side? What will be k times x plus k times y? Well, x is ordered pair AB, so k times that will be k times a, 0. And the other one will be k times b, 0. And when we add these two, the usual way we add vectors in this structure, we will get k times a plus k times b, and in the other component we need to have 0 plus 0. And now the question is whether this ordered pair is equal or not to that one. And the answer is, well, of course it is, because a similar law that we're trying to establish here for scalar multiplication and addition of vectors holds for real multiplication of real numbers and addition of real numbers. Look, this thing is equal to that thing. It's a similar law, isn't it? And also 0 is equal to 0 plus 0. We need both components of the ordered pairs to be equal in order for the ordered pairs to be equal, right? So we do come to the conclusion that the left-hand side is equal to the right-hand side. And so this axiom, just like all the others we checked so far, turns out to hold true. Great. Let's move on to the next axiom. Which states that given now two scalars, k1 and k2, and a certain vector x, if we first add k1 and k2 together and then multiply that by the vector, that should be the same as k1 times x plus k2 times x. This axiom is quite similar to the previous one, except that here we are adding the scalars and then multiplying the result by the vector, whereas in the other case we were adding two vectors and multiplying the result by a single scalar. A similar calculation as we used above would actually show that this equality is true. Well, let's get convinced of this. So suppose x is some ordered pair AB, and then what we need to check is the left-hand side being equal to the right-hand side. So perhaps now with a bit more experience in these things, we can try to start with the left-hand side and get to the right-hand side in one go. Okay, so k1 plus k2 times x will be equal to k1 plus k2 times ab. Well, now here we can treat this thing as one scalar. And the rule of multiplying a scalar with a ordered pair, the one that we invented, according to that rule, this needs to be that scalar, k1 plus k2, times the first component of the ordered pair, and then the second component becomes 0. With the property of addition and multiplication of real numbers, this is the same as k1 times a plus k2 times a and 0. And here we can use the definition of ordered pair of the sum of two ordered pairs to split this up in two. But before we split anything up, we should remark that we can rewrite this in the following way, where on the right hand side we replace 0 with 0 plus 0. Then we can continue the calculation and split up the ordered pair into sum of two ordered pairs, k1 times a, comma 0, and k2 times a, comma 0. You see, this step here was a bit kind of tricky step. We might not have thought about this if we didn't have the experience from the previous example where we saw how applying the same rules as we did for that we want to establish for vectors, applying those rules for real numbers, and then basically using the laws of addition that we defined to go back to the answer allows us to complete the proof. So at this point where we simplified everything, so when we are at this point of everything being simplified, well, actually at that point when everything has been simplified, and now I'm wondering, okay, what can I do next? And I'm thinking, oh, wait a second, so maybe I can, at this point, I know at some point I should use the way addition was defined for vectors, so maybe I can represent this as a sum of two vectors and kind of get to that step. Of course, representing 0 as sum of 0 and 0 will be essential here because, and not just that it will be essential, it will also kind of give me a hint of what to do next, but it will be essential because otherwise we would not be able to directly apply the law of adding vectors that we've come up with in this structure. But if it seems a bit overwhelming and too complicated, then the best strategy is to work out the left-hand side, work out the right-hand side separately, and then try to compare them, like we did in the previous case. Okay, so we can then continue this, and now we also go backwards. So we went backwards in terms of definition of addition. Now we want to go backwards in terms of definition of scalar multiplication, and write this as k1 times ab plus k2 times ab. And then this is equal to k1 times x plus k2 times x, and we are done. Why? Because we wanted to show that the left-hand side equals to the right-hand side, and now we have a chain of equalities which connect the left-hand side with the right-hand side. Great. We've got two more axioms to check. The next one is the following. So in this axiom, we're going to have three objects as before, but instead of mixing a multiplication and addition, we're only going to have multiplication. So let's say we have two scalars, k1 and k2, and a vector x. The axiom says that k1 times k2 times x must be the same as k1 times k2, that thing times x. And so if x is a vector of the form ab, we can calculate k1 times k2 times x to be, okay, so when we do the calculations in mathematics, we obviously want to work out the inside part first and then go more and more outside in the expression. So the inside part here is k2 times x. And then we want to write this out as k2 times ab, because that's the representation of x we need in order to proceed with the calculations, right? And then k2 times ab, by the rule we defined, scalar multiplication, will be k2 times a, comma 0. And so, again, now we have unnecessary brackets here. We can remove them. And then we apply the rule of scalar multiplication second time, where now in this case we are working with an ordered pair where the second component is already 0, right? And the first component is some real number, namely k2 times a. So by the rule, we have to multiply that first component by k1 to get k1 times that vector. So it will be k1 times k2 times a, 0. And perhaps in this case, I'm not going to be so brave as to go backwards and rather work out the right-hand side in the forward way. And so then I'll have k1 times k2 times x equals k1 times k2 times ab. And what's going on here is that now I'm treating this whole thing as one scalar. And so by definition of scalar multiplication, this will be that whole thing, which is one scalar, times the first component, and the second component is 0. And what we end up with is, of course, something that is very close to the thing we got in the previous case, and indeed they're equal by the rule of associativity for multiplication of real numbers. These two expressions represent the same real number. And of course, 0 is equal to 0, and so the ordered pairs are equal, and therefore the two sides of the equality we wanted to prove are actually equal to each other. All of this hard work, it's now 32 minutes into the movie. I hope that the last axiom will also work out just as well. Let's see. Or maybe it shouldn't. Otherwise, life is not interesting, right? If everything works out just perfectly well. If 9 out of 10 times things work out well, then life is both good and interesting. But if 10 out of 10 times everything works out well, then perhaps it is good, but not very interesting. Okay, so never mind if you don't agree with this philosophy. I'm not sure I agree with it myself. The last axiom talks about a single vector, which, when we multiply that by 1, by number 1, has to be equal to that vector again. So if a vector is an ordered pair AB, what we're demanding now is that 1 times AB must be AB. Let's see. What is 1 times AB? Well, it is 1 times A, 1 times B, right? Not at all, right? Not at all, because the way we define scalar multiplication, when we multiply a number by an ordered pair, in the second component, we need to keep 0. And that, unfortunately, isn't equal to AB. Because, okay, well, this is equal to that, but 0 isn't equal to B. Well, you might say it's equal to B when B is 0, but remember, we need to have this for all possible ABs, for all possible vectors in the structure. As long as there are some for which the equality fails, the whole axiom fails. The axiom doesn't say for some x's the equality works. The axiom says for all the x's the equality works. In mathematics, to emphasize that something works for everything inside a given set, we use the symbol upside down A to represent for all. For all x, we need to have, for all x in V, we need to have 1 times x equals x, not just 1 times x equals x for some x. And it is not true that for all x it's equal, these two things are equal. Why not? Well, for example, we could actually give a specific example, right? We could take x equals 1, 1. Then 1 times 1, 1 will be equal to 1, 0. And is not equal 2, 1, 1. So this last axiom is the one that breaks, and therefore the structure we identified in the beginning fails to be a vector space. And in case you're wondering why did we do all the work to get to a failed answer, well, that was the whole purpose of it, to see how we could, on a given example, how we could find an axiom that fails. And it is important to know how to do that, because if you don't know how to find what fails, then you will never know whether what you have for sure is true or not. Great. That's the end of the example of this video. Just a warning remark. The way we defined operations in this structure was just for the sake of this example, and that's not the usual way things are defined. So when we usually work with this space, R squared, and when we say k times AB, we don't mean k times A comma 0. And now we also know why we don't want to mean that, because that's not going to give us a vector space. Great, thank you for watching the video, and I hope everything was fine in it, and if it wasn't, I encourage you to go through it again.